Okay, then let me get us started a little bit on graphs and we'll keep going on Friday. So, graphs are fun. So, we're going to talk today about directed graphs and, well, we won't really cover these things, but we'll start talking about acyclic graphs and something called topological sort. Okay, so graphs, if you haven't been exposed to it before, so you have these points, these vertices, and then you have edges that represent connections between points. There's two types. One is sort of what we call undirected. There's no arrows, so it's just like a mutual connection between the 2 points. Another is directed from point A to point B, right? It's like a one-way road versus a two-way road. Okay, so okay. So, I mean, you guys have all seen pictures of like the internet and social graphs and stuff. So you've all seen pictures of graphs before. There's two different ways to represent them, or there's more than two ways, but here's the standard ways to represent it. So one is as an adjacency list. So for each vertex V, I can make a list of all the edges that leave V. Okay. So this is going to U and R and S or whatever. And the other is called like an adjacency matrix. So here I'll have like vertices by vertices. And in the table, I'll say, oh, a 1 in this table means I can go from, I guess, U to V. Okay. So usually it's an adjacency list. Given an adjacency list, you can build out a matrix. It's not a big deal. Okay. So what's more fun is playing with graphs. So, okay. So the first kind of graph we'll look at is a particularly nice kind. It's called an acyclic graph. Okay. So a cycle is when you can walk around and come back to the same place. So acyclic means no cycles. Okay, and that's the only thing. A vertex that doesn't have anyone coming in, it only has edges going out, that's called a source. And in a vertex where nothing goes out is called a sink. Okay. Now a DAG, for example, always has at least one sink. Why? Yeah, and where does it kind of come in? Just start at any vertex, right? And if it's not a sink, then you can find some neighbor. You can walk to another vertex, right? If this is not a sink, you can walk to another vertex. And if there's no cycles, you'll never come back to the same vertex. So if you keep walking, then you're going to keep finding new vertices, right? But there's only n vertices, so eventually you must find a sink. Same with source. You can go in reverse. No, there can be more than one sink. If I erase this edge, now this is also a sink. Okay. So an example where DAGs show up are circuits. So like XOR, XOR is when true and false gives you true, and false and true gives you true, but true and true gives you false, and false gives you false. So that can be modeled as a circuit like this, or you could do something more sophisticated like addition. So this will take like 4 bits, 1 bit here, 1 bit here, 1 bit here, 1 bit here. It's going to return true only if x1 plus x2 is equal to x3, x4 as a 2-bit number. Okay, so I think this is correct. I worked it out carefully once. So now circuits are always directed acyclic graphs where the nodes are labeled by some kind of logical gate. So and or not. These are all your standard Boolean operations. Okay. So here's my question to you. Imagine you have bits, right? And you're trying to make a computer program to simulate or evaluate a circuit, right? So, all this information is kind of given to you. conceptually, how would I evaluate the circuit? Or like if I put bits here, where would your eyes go? Something like this or something, right? Sorry? But in what direction? Along the arcs, yeah, but you probably, like, you wouldn't start here, right? You go bottom up, right? So you would, say, oh, this is 1 and this is 0. And you would figure out that this is 1 before you flip the bit and realize this is 0, right? So if you want to process this one, you need to process these two. If you want to process these two, you. So you probably go bottom up. I think that's what most people would do here. Okay? So what we can do, right? So this is sort of saying like, okay, this node here, this and you want to evaluate this bit first. You need that information to evaluate this, right? To evaluate this node labeled 9, you need to evaluate the one labeled 5 and the one labeled 4 first, right? Or else you won't be able to figure it out. So what we can do is we can think of each directed edge as giving like a partial ordering. You have to do this one before that one, right? And there's no cycles, so there's actually no ties, right? So there's different ways to enumerate. I didn't have to make x1 1. X2 could have also come first, right? But this is enumerating in a way so that the smaller numbers are kind of going, as you increase numbers, you're going up. So this is called a topological ordering. Any listing of the vertices that's consistent with the edges. So this is accurate, and if you look at all the arrows, they're going from left to right. Okay, I need just a couple of minutes to make a point. So let's say you're looking at a DAG. I promise it's a DAG. Could be, in the form of a circuit. How might you compute a topological ordering? Yeah. Yeah, so you'd probably ask what comes first, and that's a source, because it can't have any arrows coming in. So you might say, oh, here's 1, and here's 2, right? And now, as I remove those from the graph, right, and I remove the connecting edges, now you have new sources, right? So you can just keep removing sources, 3, 4, 5, sorry, and so forth. And I think this is what you mean by work list, etc. Okay, so you can iteratively remove sources from the graph, and you'll keep finding more sources because there's no DAGs introduced. I mean, there's no cycles introduced, right? So still a DAG still has a source. So that's one way to topologically sort the graph is to repeatedly remove. Okay, so that's one way to kind of sort a DAG. So you can do this while you repeatedly find the source, and you can even make it run fast. So to identify a source, it's a vertex with no outgoing edges, right? So I guess you should actually keep track of out degrees. So you might say, oh, initially I'll count up for every vertex how many edges leave it. Oh no, how many edges enter? It should be in degree. I'm sorry. It was in degree. And you say, oh, a source is anything with 0 in degree. And I remove a source. When I remove a source, I delete some edges, and I can go to those vertices and update their in degrees, which go down. Yeah. Oh, yeah, I could have also like removed sinks one at a time. Yeah. That's okay. That's true. But I'm going to be consistent with removing sources, in which case you're counting in degrees. And you keep track, you do linear time. Okay. So next time what we're going to talk about is how to do something similar in a graph that has cycles. So we're going to try to order the vertices so that if it's in a cycle, then it's just kind of tied. But otherwise, you can distinguish things that aren't in cycles with each other and stuff like this. So this will get more sophisticated. We'll also study something called depth first search and so forth. Okay, so that's what we'll do on Friday. Thanks, guys. Okay, then let me first. So we started last time discuss this discussion on graph algorithms. So I'll just recap and get us caught up as maybe a few more people trickle in. So now today we'll really do all of these topics. And yeah, so the graphs are these combinatorial objects. I'm sure most of you have seen them in some form before. You've definitely seen pictures of them. And we can represent them with lists or adjacency matrices. And what we discussed last time was these graphs with no cycles in them. And for example, they come up when you look at circuits. And when you ask yourself how to evaluate a circuit or something, you might evaluate them from bottom up naturally. And that has a name. That's called a topological ordering. So I think of like if U has an edge to V, then that's like saying U is less than or equal to V, and then there's some transitive properties. And so you can try to line up the vertices so all the edges are pointed in the same direction. It's not necessarily unique. There may be several orderings like this. And we talked about how to compute one of these things, and this is sort of the bloody remains of our algorithm. But the idea was to keep removing sources, which are vertices that don't have any integrity, and just putting them at the beginning. So that was what we did. And you could do this in linear time, and that's where we left off. All right. So let's talk about searching graphs. Okay, so this is my daily challenge. My office is in this building, and somehow I have to make it to here. Actually, it's not so bad this year. Other years it's been a little bit further. And so I pull up Google Maps and I try to figure out how to go from point A to point B. So like, you go here and then like sometimes I jaywalk here, like it takes a while these days. And then like I've learned to sort of walk on the street to avoid people. There's not many cars over here, so I kind of take this weird zigzag and it doesn't matter. Okay. Um, fine. If it was the first day of school, then I got into the walk center. I got up to the third floor, and then I took the longest possible path to find this room. Okay. So, the point I'm making is that, okay, you have a map. There's point A, point B. You want to find algorithms to get from point A to point B. And, okay, so here's maybe a more fun one that I once found on the internet. So here's the puzzle. So you start with this yellow cat in the top left corner, and you want to make it to the white cat in the bottom right corner. Okay? And you can only go from like a forward-facing cat to a backwards-facing cat. Where a forward-facing cat is just a cat facing the front or the cat facing the back, and I guess it's given away by the eyes. Okay? So your goal is to try to figure out how to get from start to finish. I'll give you a couple minutes. Okay, who thinks there's no path? Or alternatively hasn't found a path yet? It's hard to prove there's no path. It's something called co-NP. And who found the path? Okay. Well, let me just do how far did the people who got stuck get? So I'll start here and I'll just trace, I was going to do it in red, but that might look violent. I'll do it in yellow. Because I'll just trace a path, so I assume I should go down and left initially. And then I guess this is also kind of forced. Okay, now should I go down or to the right? Just pick one. Right? Okay. Your right is my left, so that's okay. And then to the right or down right-ish. Okay. And then I guess to the right, and then I guess down or up. Okay, now you have three choices: left, right, or down. Okay, and then like down left or down? Down. Okay, and then down. Okay, and should I go down again? Guess this seems to be connected. Down and then right. I guess you can go one more to the right. This is where people got stuck. Okay. All right. Who figured this out? Now where do you go? Oh, we can go back. Okay. I can take back our last few steps. I don't know how far you want me to go back. Tell me when to stop. Yeah. Uh. Oh, down. Okay. That white cat has its eyes. It's facing you. Should I start backtracking again? Tell me when to stop. So no one figured this out. We can't spend all class on this, unfortunately. Do you want to bet money or homework points? You can give up one of your n over 5 problems. In exchange, I'll give you a free problem if you're right. Yeah. So do you want to bet money? Okay. All right. I'll never collect it from you because you're grad students, but here's the trick. There's one more cat. Yeah. Okay. Yay, okay. Uh, and then, how do you finish again? Oh, now you go white, yellow, white, yellow, white. Okay. That was the trick. All right. Okay. Making money off grad students. All right. Okay. So another version of the problem is you start at a vertex S and you ask, can it reach all the other vertices? Okay. No hidden cats here. Just 20 vertices, 12 vertices or something. Not a big graph. So I won't give you as much time. I'll give a few, look at a little bit and then I'll do a yes, no vote. Okay. Who's not voting? Okay. Who thinks that S can reach everything? Oh. And who doesn't think S can reach everything? Okay. All right. So N minus 3. Liars. Okay. So in fact, the answer is no. And these three vertices in the middle, there's a little triangle where all the edges point outwards. Okay. So whatever. But I think this is only a few vertices, right? This is like 10, 12 vertices. So even these small examples show, okay, these are kind of tricky. And now we want to figure out how to do this automatically, right? Given a graph, try to figure out if S can reach everything. So that's what we'll do first. Okay, and I don't know if this perspective is very helpful, but sometimes when we think of a maze or a map or something, we often imagine a bird's eye view. And I want to suggest that a computer is always like a little bit more myopic. I feel like when you make these algorithms, it's almost like you're in the maze or something compared to being able to see a maze from a top-down point of view, right? Because the computer only examines one piece of information in each step. So it's not so obvious, even if you know the eventual answer. Okay, What was this slide supposed to be about? Okay. Um, so the setup is, all right. Okay. So the input is just this graph, and you have 2 points S and T. I want to know if S can reach T. That's how we'll frame it. And I wanted to make this clear because the first step I was going to have us do is to define, we're going to try to do it recursively. Okay. So we're going to try to define a recursive spec. Okay. Does anyone want to propose an idea? Yeah. We start with a sentence. Just give me any sentence with some parameters. Okay, that sounds good. So I'll call it recursive search or something, just to point out that we're going to do recursively first. It's going to return true if you can reach and false otherwise. Okay. And now if we want to implement this, you might say, okay, so maybe here's a possibility, right? So if S can already reach T, then we just return true. Otherwise, I'll start looking, I'll check all the edges leaving S. Okay, so I'll say, okay, I want to get from S to T, I'll use a different color. I want to get from S to T, and S is not equal to T, so I'll recursively call this one, and I'll recursively call this one, and recursively call this one. And if any of those can reach T, then we should return true, right? Okay, so that sort of like follows a template of what we've been doing, but there's some issues, yeah. Yeah, so okay. So at some level, this looks not so unfamiliar from what I've been encouraging us to do in the past few classes, but so somewhere it doesn't quite work, right? So there's some kind of, did I draw it? Okay, so, all right, so is that coming up? Yeah, so in particular, this is the kind of argument we want to have said, oh, if S cannot reach T, if S can reach T, but S is not equal to T, I should say T, not V, then there must be some other edge SV where V can reach T and I'll try one of them, right? That's like so what's the flaw? The flaw pointed out is like, well, what happens if you do this, right? Our recursive algorithm would just go around and around and around. It would never even finish, okay? Let alone come to some conclusion or another. So somewhere, modulo that typo, which I can fix, where did we cheat, right? This looks like something that follows the form of what we've been doing, but obviously the algorithm doesn't work. So what's the flaw? Yeah, and so in particular, we don't really, have a base case. We don't have an ordering of cases anywhere, right? We're not actually making progress in a meaningful way. And that's the issue, which I know you have seen this algorithm before, so you identify with marking, but the real issue is that there's no kind of actual inductive step being done. Okay, so you can use recursive in the wrong way. So, okay, that's sort of our conceptual question, right? Recursion really requires induction to be correct, which means that something needs to be as smaller, you need to reach some kind of base case or something like this, right? So even though this sentence sounds correct based on our kind of recursive sentence and stuff like this, it's not because we're not properly using induction. So our question is how to fix this. Okay, so if you were doing a maze, right? Like sometimes American restaurants, if you're a kid, they give you like a placemat with a maze on it and stuff. Those mazes are much harder to do if you don't have a crayon. You're just trying to like eyeball it all the way through and stuff, right? If you're actually doing it, you take your crayon and you start tracing out things you've already explored, right? And you keep track of where you've been and where you hadn't been. And then you're more likely to solve a maze for children. So that's what we're going to do. Okay. So You've all probably seen this before, but nonetheless, when I visit I'm going to keep track of marks on vertices. Okay, initially everything's unmarked, and marking means I visited it. Okay, like a breadcrumb. So I'll start at the vertex S, and this is not marked yet. So let me first mark it, and then I'm going to start exploring. Okay, so we'll explore this edge, and it's not marked yet. We mark it, and then we start exploring some more. I mark this, I explore, I mark it, and also I back out because there's no more edges to explore. I explore, mark it, explore, mark it, explore, mark it, and so forth. Let me get to a more interesting point. Explore, mark this, and then you start backtracking. So I finished that, I finished that, I back out of this recursive call. I guess I also back out of this recursive call. I back out of this recursive call. Oh, I don't back out yet, but I am here at this point, and then I find one more edge I haven't found yet. Mark it, back out. Now I finish, I back out, and now I'm back to the top. I might have missed an arc or something, but hopefully I didn't. And now it's going to choose another edge I haven't explored yet, like this one. And finally, we get to a point where the marks actually matter. So this vertex will try this vertex, right? But I've already explored this vertex and marked it. So it's going to go down, but it's not going to continue. It'll just go back up right away. Okay, and then you'll keep, you'll bubble back up, and then you go this way. Okay, so in this way, we'll make sure we only explore a vertex once. By explore, I mean really search through the arcs leaving it. Yeah. 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 So if I had done it in different order, then I would eventually get to this vertex from a different route, right? And from there, I would continue searching or something like this, right? Well, yeah, let's expand then and try to clean up our intuition. Because I'm guessing many people who have taken some form of algorithm have seen this algorithm before. And so in the back of your mind, you're like, oh, it's supposed to be the correct one. But maybe let's walk through and try to understand it. Okay. So here are our two claims. One is that it's fast, it'll run in linear time, m plus n, where m is the number of edges, n is the number of vertices. That's the convention in this class. And the more interesting thing is to show that it does visit all the vertices reachable from wherever you started. Okay. All right. Why is the running time good? Why is it linear time? Yeah, and in particular, I'm only going to look at this edge, for example, right after marking this vertex. Okay, so that ensures, and I only mark each vertex once, so I end up only exploring each edge once. Technically, m and n could be replaced by the number of edges that s can reach and the number of vertices that n can reach, because other things will never get touched. But, okay, so more interesting reason is why it's correct, or maybe in particular, how to articulate that it's correct, right? Because maybe you feel like that's intuitive, and now we just want to give one way of putting it into words. There may be more than one way to do this. Okay. So here's the setup, right? So all I know right now is that all the vertex, the graph ran. The algorithm ran on a graph. Okay. And I feel like I know what it's supposed to do. I'm just trying to nail it down and really establish it does what I expect and marks everything that's supposed to be reachable. Okay. So, okay. So first of all, everyone that is marked is reachable. right? Because I took some path to get there. So I'll take that as a fact. And now what I'm going to do is I'm going to take all the vertices and split it into two sets. Okay. A is the vertices that are marked by the algorithm. Just after you look and some were marked. And then B is everything that's not marked. I want to show that A is the same as the reachable set, but that we haven't established yet. Okay. So suppose there's some vertex W that is reachable from V. I can get from V to W, but for some reason it wasn't marked. Okay, so I'm setting up a contradiction. So here's something that opposes the statement I want to prove, and now I want to argue that's impossible, which means that everything reachable would have been marked, and that's what we want. Okay, so I've just drawn a picture like that. Okay, now all I know about V and W is that there's some way to go from V to W, right? So there exists some path or some walk through the graph, right? Something like this, okay? Which means that somewhere along the way on this path starts in red and ends in blue. Red, 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 and at the end it goes blue, blue, blue. Okay? So there must be somewhere along the sequence where you went red and then blue. Okay, so there must have been some vertex, some directed edge A, from A to B or something, where A is marked and B is unmarked, just because the path starts in marked land and ends in unmarked land. Okay. So that means there's some directed edge from A to B that's going from marked to unmarked. Okay. And now what's the problem? Yeah, and in particular, as soon as I mark A, the algorithm is going to explore every edge leaving A and mark the opposing vertex. So that's our contradiction. That's what we're showing. But just to put it into words, I set up a proof by contradiction. I think this is probably intuitive as an idea, and it's really more an exercise of, oh, how do I articulate it? Yeah. Mm-hmm. Uh, there's probably some of those things that I said out loud and didn't write down because beyond a certain point you stop reading the slide, right? So statements like when I said, oh, depth first search is only following edges, so every vertex that's marked is also reachable. I might write out if I wasn't worried about like killing you out of boredom, right? But that might be worth stating just to be clear. I mean, yeah, we can look at this, right? Otherwise, I think it's pretty clear. You might write them as sentences instead of just bullet points. You know, I set up the marked and unmarked, and I clearly stated the contradiction I'm going for, right? So this first four part reinforced by this picture, there's some marked, some unmarked, and I'm assuming by contradiction that there's a reachable vertex that was unmarked. That you definitely have to say. You should be very clear about if you're doing a proof by contradiction. What is the thing that the contradiction you're setting up and make that clear? And then I think this part's kind of okay. Definition of reachability means there is a path from V to W. So maybe I could have wrote by definition by reachability, there's a path from V to W. And then I think this is okay. Since the path starts in A and ends in B, there must be some arc going from set A to set B. Yeah, I think this would have been kind of okay. Maybe that sentence where I said everything is marked, it must be reachable, should have been there. Okay. It's a little, yeah. We try to use our best judgment, and then we'll negotiate with regrade requests when there's controversy, and yeah. Okay. So that's what we showed, these two things. And maybe more precisely, because this will come up, depth first search from a vertex is only going to finish after guaranteeing that every vertex reachable from V has been marked. Okay. Yeah. No. No. You. Yeah. So there's no else statement. So if V is marked, you just terminate. You just run away. So you're not trying to find a particular way from S to T. You just want to know if there is a way, right? So if you found some other way to get to the middle, and the middle found some way to get to T, the answer is yes. It'll still work. That's what we proved. The situation you're describing is impossible. Okay. Why did I leave this blank? I don't know. Okay. Good. That's searching graphs. Let's talk about sorting graphs. This will come back to topological ordering. Okay, so we talked about how when there's no cycles, you have this natural notion of trying to line things up so all the edges go in one direction. Okay. Now, okay, so what we're going to do is try to think of an alternative algorithm to the one we came up with on Wednesday. Okay. So what we kind of showed, or maybe this is a proof, but between the time that V is marked and I first enter and start exploring V, and the call to V exits, depth first search is only going to search the vertices that are reachable from the vertex. So given that, let's look at the following situation. So let's say that I have two vertices V and W. Okay, and there's a little bit of asymmetry. V can reach W. Okay. And W cannot reach V. So there is no path like this. So that kind of asymmetric situation. The claim is that any depth first search, there might be some depth first search that starts from something way out here or something, right? And it's going around and exploring and stuff. And it might encounter V and W at different points. Okay? Any depth first search that explores both V and W must finish searching W before it finishes V. Okay, so that's what we want to prove. Okay. Mm-hmm. So okay, it explores V and W. So at some point, starting from some other vertex, you did call DFS V and DFS W. And who knows actually which one came first? Okay. And what I'm interested in is when those recursive calls end. So the call ends when sort of you just finish the code inside. It's not tail recursive, so it's really when you finish exploring all the edges. And you back out. So I imagine it's on like a stack. Okay. So we're going to prove this. So what we're going to do is we're just going to establish more properties about that's for search, and then we'll really put it to use. Okay. So I set it up with two cases. What are two natural cases, or what's a natural way to break it into cases? Yeah. Yeah. So that's how we'll do it. We'll look at whether V got marked first or W got marked first. Okay, we'll just do each one separately. So what happens if V gets marked first? Well, we know that depth first search is only going to terminate after everyone that's reachable from V is marked. That's what we did earlier. Okay. So I thought it was written. Okay, good. Um, so depth first search is going to mark W because it guarantees that everything is going to visit everything reachable from V, and it'll finish it before finishing V. Okay. I just wrote the notes. I never read them. Okay. It'll mark W and it'll finish. It has to finish because it has to do the inside calls before it backs back out. Okay. In the second case, when it marks W first, then the depth first search at W is only going to search those vertices that are reachable from W before finishing, and we're in this situation that it excludes V. Okay, so again, maybe this is not too surprising, or this was already intuitive to you, so this is just trying to articulate it and get it down. Okay. So let's keep using this property. Okay. And now let's look at this algorithm. So imagine, so in other words, what I'm saying is that this depth first search algorithm, which is sort of intuitive marking Hansel and Gretel kind of algorithm, now has this is well behaved in a certain sense, right? Sort of, it is kind of wild. It chooses arbitrary neighbors to explore next and stuff. But no matter how you go about it, you have this nice property that when you look at which vertices are finished exploring, you always have some ordering that's somewhat related to the reachability. If V can reach W, but W cannot reach V, you have this nice guarantee. So let's look at an algorithm that prints out vertices as we finish, and then study that ordering. Okay, so this is just like before. This is called a post DFS ordering because it's like post is like after, and it's like on the way out. So you keep doing the recursive thing, but after you finish exploring the vertex, I'll just like print out the vertex, append it to some kind of output. Okay, and this might not explore everybody. V can only reach some vertices, so I'll just wrap it in a whole loop and call it on all the vertices. So if a vertex is already marked, it'll just terminate right away. There's nothing to do. But this will make sure that everyone gets printed out eventually. Okay, so this is often happens where you have really an interesting piece of code, and then you just like have some outer loop, and we just call that a driver or something. There's other names for it. Okay. So we're going to study this ordering. Okay. So look at what happens on a DAG, right? So in a DAG, if U can reach V, V cannot reach U, but why? It's acyclic, so you would get a cycle. Okay, so that means if I did the post DFS and thought through what this lemma tells us, every time U can reach V, V will get printed before U. Right? So if I printed the vertices out in order and afterwards drew the edges, they would all have to go this way. Okay? Because of that previous argument. So this gives us a second algorithm to compute a topological ordering of a DAG. You could run DFS and use this post DFS ordering. That'll also give you an ordering. Okay. So that's kind of interesting. That's less obvious than I think pulling out sources and sinks. It's sort of a funny way to compute a topological ordering. Okay. But it's going to be more useful, or we're going to actually be able to do something stronger next. All right. So now I want to look at graphs where you can have cycles. Okay, that means A can reach B and B can reach A. Okay, so in that case, sometimes one terminology for this is to say it's strongly connected. Two vertices are strongly connected if you can go there and back. Okay, and sometimes a whole graph is strongly connected if everyone can reach each other in every direction, there and back. Okay, So strong connectivity, right, defines an equivalence class. So the rules of equivalence class is like, okay, if A is strongly connected to B, then B is also strongly connected to A. It's symmetric, okay? And it's also transitive. So if U is strongly connected to V, so I can go back, and V is strongly connected to W, so I can go back, then U is strongly connected to W because I can go from U to V to W, and meanwhile I can go from W to V to U. Okay. Yeah. Yeah. Sure. Let me go back. So, uh, so this algorithm is just doing marking. Maybe this is a better slide. Yeah. So this is just marking the vertices just like before. So it's the same reason that depth first search took m plus n time. So the reason that depth first search was so efficient is that do I have any pictures? Pictures. Something like here, right? Um, I go here and then I mark it, right? I check it off before exploring, and then I look at the edges that leave it. This way, later when I go like this and I go here and then I go this way, I say, oh, I've already seen this vertex, so I don't visit it again. But that means every arc that leaves this vertex, I only look at it after marking it, and I only mark it once. So that tells you, oh, I only look at every edge once. Yeah. Okay. Let me get us back. Okay, so strong connectivity is this like equivalence class, right? And so it would be nice to sort of group the vertices into their strongly connected components. So in this graph, I've colored in different colors the strongly connected components. So we have this triangle cycle, so they can all reach each other. This yellow part is like some union of two cycles, but they can all reach each other. The green triangles, green triangle, they can all reach each other. That's another strongly connected component. And then these two sinks can't reach anybody, so they're just by themselves. Okay. So one thing nice is that like all the purple have the same connectivity relation to all the yellow, right? So if you can identify the strongly connected components and kind of compress it, then you're preserving all the reachability information, but the graph gets smaller and stuff like this. Anyway, it's a natural question to ask. Can we figure out how to compute this? Okay. All right. So good, good. So I'll start with a baby version of the question. Given a vertex, how could I find the strongly connected component of that vertex? My goal is eventually to find all of them. So any ideas? Okay. So first I can run depth first search from V. So BFS will also find you vertices reachable from V. We haven't talked about it yet. But in this step, what you've done is you've figured out everyone that V can reach. But the strongly connected components of V is going to be the vertices that can also go back. So that's the next step to fill in, right? So how can I figure out who can reach V? Sorry? Okay, so I can like somehow try to identify like if my search goes back like this, then I know everything is on the cycle. Okay. Now, what happens if like my search goes back like this or something? It's only part way. That's a little bit complicated, right? So, if you have something like this, then actually this can go back to V, but it's going to be a little messy to code this, right? It's a lot of state. Yeah. Maybe the whole graph is strongly connected. There's no source or sink. Yeah. Yeah, so I can call depth first search from every vertex I found was depth first search V. I guess the leaves would also suffice, but then you have to do a little more work. But you can imagine just running depth first search from everyone else and then figure out which of those vertices can reach V, right? So that'll take like n depth first searches in the worst case because you're basically running it from everybody. Can anyone figure out how to do this in one more depth first search? Yeah. So this is great. This is going to help you on a lot of homeworks and problems, okay? Sometimes the answer isn't to make a new algorithm, it's just to change the input. Don't change the algorithm, change the input. Because the nice thing is we've already analyzed depth first search. We're very comfortable with its properties. And so I can just understand how the input changed and I get all the lemmas and proofs and all that for free. So we're going to run depth first search from V in the reversed graph, right? So that's really kind of going to try to figure out everyone that can reach V and stuff like this. Okay, so if V can reach X in the reverse graph, then when I unreverse it, that means X can reach V. And then you just output, the set of vertices in between both of them, right? Okay, so then you just compare the two lists. Okay, so good. Now, okay, that's nice because one strongly connected component is going to take m plus n time. And now if I want to get all of them, I'll need something like mn time. Let's say m is at least n, right? Because every vertex I might have to like go search a lot of vertices and then find out that very few of them come back and stuff like this. Okay, yeah. Uh, sure. I guess that's folded into here. So it'll take linear time to just rewrite, go through every edge A, B, and then write a new one called BA. Yeah. Well, M is the number of edges. Oh, okay. So here I got a little bit lazy and I said, okay, just between me and you, let's say that M is at least N. So if every if every vertex has at least one edge leaving, then M is at least N. And those vertices by itself, you can just of M squared, N. Oh, well, M could be bigger than N, right? M can be N squared even. Well, that's not even bigger than this, right? That's smaller than this. If M is N squared, you get N cubed. So I'll write Mn. Maybe I should just not create confusion and write plus N squared. Okay. But anyway. Okay. So our goal is to try to do better than that, which is already non-trivial because we had this trick of reversing the graph. Okay. So, all right. So here's where I took the strongly connected components, right? And they're all equivalent when it comes to connectivity. They're not distinguished. So what if I thought of each of them as a vertex? So I kind of shrink the component and I have an edge from like the green component to the purple if there's at least one edge from some green vertex to some purple vertex. Since all of these are connected to each other and connected to each other, this will still preserve the overall pairwise connectivity. Okay? So, in this smaller graph, we sometimes call this the graph of strongly connected components. There's something special about it. It's a DAG. There can't be a cycle because if there's like a cycle between, I don't know, these three, suddenly they're all strongly connected with each other and they would collapse. Okay? So there's no cycles in this graph. And if there's no cycles, well, okay. So So our current approach is like, if I put the whole thing into a loop, I'll keep choosing any vertex and maybe compute its strongly connected component from what we did before. Okay. And I'll label all those vertices I found in the strongly connected component, say, oh, that's all in the same component with each other or something. I'll output it somehow. And then I can remove them from the graph. Okay, so we'll start there. So that's one way to try to build an algorithm. Now, if I wanted to make it fast, if I wanted to make this fast, which vertex, well, okay, how about this? Suppose, magically, and we don't know how to do this yet. So when I'm pulling one vertex at a time to find a strongly connected component, okay, suppose I was always able to find a sinc component. Like suppose I started here, right? And you're just able to magically identify a vertex from a sinc component. We haven't figured that out yet, but imagine you could, right? If you're promised a vertex is in a sinc component, how would you find its strongly connected component? You could do what you did before, but it's actually easier now. If I just run one DFS, anyone it can reach is going to be in that sinc component. So maybe this is not a good example because it's just a vertex. So let me suppose I erased this red vertex, right? Now if I ran, now purple is a sinc component. And if I ran depth first search from any vertex in purple, it can't escape purple because purple is a sinc component. And anyone it can reach is if A is connected to B and they're in the same strongly connected component, then B can reach A. Okay? So if we were able to magically identify vertices of sinc components, then I can actually make this easier and only run depth first search. So, right. So in principle, we could do something like this. I'll call it sinc first strongly connected component, where I keep magically identifying a vertex in a sinc component, running depth first search. It can never leave the sinc component. And then I'll remove it from the graph after doing it. So there'll be new sinc components afterwards. So this is sort of similar to us removing sincs one at a time before. Okay. Now, the really great thing is that if I run depth first search from a sinc component, I never leave the sinc component. I'm not looking at the rest of the graph. So I actually just look at this vertex and I remove it from the graph, right? So like this and like this. And I've only spent time proportional to the number of edges that were incident or kind of connected to that sinc component. And if I ran it in purple next, I would never leave purple. And so I'd only be visiting 3 vertices and those edges. Okay? So if you do it this way, you only visit each vertex once. So if we could magically come up with a vertex from the sinc component, then this will all add up to m plus n time. You only end up looking at each edge and each vertex once. So this could be faster. Okay? So the only issue is we don't know how to do this yet. So I think we can figure out how to do this in just a few minutes. Okay, so I'll go a little over. Okay, so this is sort of like the topological ordering of strongly connected components. And if we can kind of implicitly identify this, we'd be in great shape. So, okay, so how do we find a sinc first kind of ordering? Okay. Well, let's look at this post DFS ordering. Okay, so we were promised that if V can reach W and W cannot reach V, then W will be listed before V in any post DFS ordering. So here's one enumeration of post DFS. And if I list the vertices out and I draw it, and I did draw this correctly, you get this for that exact graph. So that's a post DFS numbering up there. I put it down here, I drew the edges. What's kind of interesting about the blue edges? There are no cycles. They're all going this way. Okay. So within a strongly connected component, it can go backwards. But across components, which are the ones labeled in blue, it's always going this way. Okay. Now, okay. So, all right, maybe just looking at this, how can I use this trick to try to identify a vertex in the source component? Yeah. It doesn't have any incident blue edges. Well, this one doesn't have any incident blue edges, but it's actually not in a. Okay. Well, okay. All the components have some blue edges, but also I think one thing to be careful about is that I've colored it here corresponding to that, but the algorithm doesn't know these colors. So it doesn't know which one, it doesn't know that this is a block of yellow. I've just drawn it, for us. So it's hard to identify which component has blue edges or not because we don't know which are the actual components. So in that sense, this picture is a little misleading. Yeah. I think once you get the edges, you'll get the whole thing. Okay, let me make this point then because we're going a little bit over. You might be tempted to think, oh, the first vertex should always be in a sink, right? But that's actually not quite true. In this exact picture, here's a sink, and this is not. Okay? But look at the other end. What do I know about the last vertex? It's always a source. It's always in the source component. So PostDFS actually doesn't give us the sink component, but it does give you something in a source component. And reverse it. Okay, it sounds like a song. So that's what we're going to do. Okay? So we are guaranteed from this lemma we did earlier that PostDFS will always put a source vertex at the end. Okay? So if we wanted a sink, we'll reverse the graph and do it. So that is ultimately the algorithm. It's very clever. So we'll compute a post-DFS ordering in the reversed graph, and then we'll keep it'll be the last, because that's going to be the source of the reverse graph. So we take the last vertex, we just do DFS, because it's really in the sink component. We label it, we rip it out. And one thing subtle is that the post-DFS ordering you computed at the beginning is still a post-DFS ordering for the remaining graph. So you can continue to reuse the same ordering of vertices. Okay, so we just do that trick, and then you're done. And you get the whole thing in m plus n time now. Okay, so it's very clever. So you can actually get all the strongly connected components and the ordering and all that in m plus n time. All right, thanks guys.